Welcome to the ICLR Friday Forum for July 22nd, 2022. I'm your host, Dr. Keith Porter. I'm Chief Engineer at the Institute for Catastrophic Loss Reduction. This is one in a monthly webinar series hosted by ICLR, Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to make Canada more disaster resilient. Today, our esteemed colleague, Dr. Tuna Onur, will summarize important changes to the latest edition of the National Building Code of Canada. These changes affect the design of new buildings to resist earthquakes. Dr. Onur is going to focus on the implications of those changes for seismic risk in Canada. You can read Dr. Onur's bio sketch in our announcement for this Friday Forum, but briefly, she serves as principal of Onur Seemann Consulting Incorporated, and she's also adjunct professor in the Department of Civil Engineering at the University of Victoria. Our webinar will last 90 minutes today. In a moment, our speaker will present for about half that time. Then I will moderate Q&A for the rest of the time. Please feel free to type any questions you have into the Q&A box, not the chat box, but the Q&A box. I will try to pose your questions to Dr. Onur in approximately the order that they're entered into the Q&A box. If we have a lot of questions, I may only pose your first question. Then I'll move on to others and then circle back for additional questions. Our webinar today is recorded. ICLR will post a link to today's talk on Monday or so. So if you have colleagues who couldn't attend, let them know. And with that, I'll ask Dr. Onur to begin her talk. Take it away.
Thank you, Keith, for the introductions. Good morning, good afternoon, everybody, depending on where you are. Like Keith mentioned, I'm going to talk a little bit about the NBC 2020, which was recently released, and its implications for seismic risk in Canada. Starting with a little bit of a history on the seismic provisions in building codes of Canada. The first time, we've had codes earlier than this, but the first time any kind of mention of seismic loads in the NBC was in 1941, and it was a single sentence simply saying, take the weight of your building, apply 10% of it as a horizontal, as a lateral load to the structure, and then analyze your structure. And that was the full seismic provisions in 1941. In 1953, we switched to a zoning map. You see on the right-hand side here. See if I can point. And it basically created 4 zones: zone 0, 1, 2, and 3. 3 had some of Western BC as well as some of Southern Quebec and Ontario. And then since then, it's been progressively getting more complex. And we now have, and as of about since 2005, so we went to a 5-year cycle roughly, starting in 1960. We've skipped a cycle in 2000, but since 2005, we've been continuing on at every 5-year cycle. And the latest code has just been released is the NBC 2020. And the seismic provisions have gotten progressively more complex over the years. So just a little bit of history. But let's focus on NBC 2020. So what's new in the building code with regards to seismic provisions? I'm going to focus broadly on three pieces of the new changes in the code. One is the new seismic hazard values. So we typically update these every 5 years along with the code. So Geological Survey of Canada and ARCAN computes these values, updates their hazard models based on the latest science and data available. And what this meant in this round is that this hazard estimates for pretty much the entire country went generally up. So we have some increases in hazard in this code cycle, most notably in the East in terms of percentage increases, mainly because the hazard there is lower, so a certain amount of increase translates to a larger percentage increase. The other change in the way the hazard values were calculated is in the past, NBC 2015 and earlier versions of the code, we had the hazard values calculated at what we call a reference ground condition. And then we would have tables in the code that would convert that into whatever the site class or site conditions your particular site had. In 2020, we got rid of this process, so the hazard is now calculated directly at the site conditions at the site. So now they can be basically queried from the Geological Survey of Canada's website by using a location and a VS30, and I'll explain a little bit what VS30 is and how it represents the site's conditions at your site. The second major change, and I'm really happy to report on this, because when I spoke at another ICLR Friday Forum exactly 10 years ago, I was mentioning to you that there's only one performance objective per type of building in the NBC, and that we hoped in the future to change that to add more performance goals to the code. And I'm happy to report NBC 2020 is the first time we've done this. So for each category of buildings, normal importance, high importance, and post-disaster buildings, actually a subset of normal importance buildings, in addition to high importance and post-disaster buildings. We now have 2 performance objectives for each of these categories of buildings. And I'll talk a little bit about that and its significance. So we now are moving, what that means is that we're moving beyond collapse prevention only, which is what we were focused on in our previous codes. And the third thing that I'll report on is basically what's not new. Unfortunately, part 9, which in our code is the housing and small buildings section of the code, was not able to be updated. So part 9 remained as is from NBC 2020, both in terms of the provisions and also in terms of the hazard. So now in the code, we have 2 separate sections of the codes using different hazard values. Part 9 for housing and small buildings, still using NBC 2015 hazard, and part 4, the engineered part of the code, uses 2020 hazard. This was not intended. This was due to a very long and arduous public review process, not being able to be finished on time for the new Part 9 provisions to go into NBC 2020. So the intent of NRC, National Research Council, is to perhaps issue a mid-cycle update between NBC 2020 and NBC 2025 to fix this kind of rift between the 2 parts of the code. All right, so focusing a little bit on about the new hazard values. By the way, I should probably mention that this may not be an important change in terms of the risk models that the industry uses in Canada. Most vendor models had already accounted for these possible changes that were coming to NBC 2020 hazard a long time ago. So this doesn't mean, and potentially doesn't mean an immediate new update to hazard incorporated into risk models in Canada. So the new hazard values in a nutshell generally increased across Canada. I show one of these maps that NRCan have on their website. This is for spectral accelerations at 0.2 seconds. What that means is it's basically showing the hazard that a low-rise building would feel. So these maps are prepared for various natural periods of vibration of buildings, and as the period gets longer, we're talking about taller and taller buildings. And there's a series of these. In practice, engineers in Canada do not use these maps. They basically enter latitude and longitude, and in NBC 2020 now the site condition, and directly get their design values from the website. Now, while the hazard increased across the country, most significant changes were in the East in terms of % increases in the hazard. And mostly these were due to updated ground motion models. So I'm going to talk a little bit about ground motion models later to explain why they're important and how they contribute to this change. Now, Southwest BC also saw some increases in hazard, again, mostly due to updated ground motion models, but also the uncertainty terms that are in these ground motion models have also been changed, and that also contributes to the change in the Southwest BC. Another major change in Southwest BC was the increased rates of the Cascadia subduction interface earthquakes. So we used to think these earthquakes happened every 500 years roughly, but that return period has come down to 430 years. So just to remind you, we're about 300 years into that cycle that we now think on average was 430 years instead of 500 years. So the activity rate of these big subduction interface earthquakes have increased in the hazard models of NBC. One other reason was the updated geometry of the subducting slab. So as we are in a subduction zone in Southwest BC, the subducting slab, the oceanic plate that subducts beneath the continental plate in Southwest BC is now, the geometry is a little bit different and it's somewhat closer to Vancouver, the edge of that slab. So therefore, the hazard is increased in Vancouver a little bit because of that. And another one that is mostly consequential for Victoria only is the addition of Leech River Valley fault to the hazard calculations. This was a fault, active fault that was identified and trenched a couple of years ago. And there were a number of earthquakes identified, slip from these earthquakes were identified in the trench, and they were dated. And therefore, we were able to get a bit of a recurrence rate on this fault that then could be put into the building code hazard values. Now, just looking at Countrywide, I selected some cities here to give you a representative feel of how hazard changed in NBC 2020 with respect to NBC 2015, starting from the east going west. And I put these percent increases in the hazard, both for a short period hazard, which mostly impacts low-rise buildings, and a long period hazard, which mostly impacts high-rise buildings. So kind of categorized it that way because us engineers, we think of hazard in terms of period of vibration of the building. And like I said, short period corresponds to the natural period of vibration of low-rise buildings, and long period hazard corresponds roughly to natural period of vibration of high-rise buildings. I also put on in the second column here overall hazard level for these communities because, for example, a 90% increase in short period hazard in Halifax may still be a fairly low hazard because to start with, the hazard level was quite low. So kind of to guide you in what to expect in terms of how significant these increases are. So there's location, overall hazard level, increase in short period hazard, and increase in long period hazard. Upon a quick glance, you'll see that most places the hazard increased about 40 to 50%, both in the short period and long period. So that's a fairly significant increase. But I should mention that this increase comes after a decrease in hazard in 2015. So in 2010, NBC, hazard was at a certain level, and NBC 2015, we went down a little bit, and 2020, we went up a bit again. So some of these hazard values are not that different from 2010 NBC hazard, even though they seem to be a significant hazard increase, particularly in the east. On the west, however, we see a steady increase in hazard as more ground motion data becomes available. These ground motion models are being updated, and also more information becomes available on active faults and also subduction zone, both geometry and recurrence rates. So Vancouver and Victoria have gone up, Vancouver more modestly than Victoria, and both of them are attributed to the subduction related changes, but also in Victoria, it's also about 10% of that change comes from the addition of the Leech River Valley fault As part of that change in hazard, like I mentioned, we no longer have these tables in the NBC 2020. So NBC 15 had the reference ground conditions, we calculated hazard, and then we had to adjust that hazard to based on what site conditions you had at your site. And those were accomplished by a series of tables for different periods of vibration and different levels of shaking and different site categories. We no longer approach this problem site effects that way. So the code no longer has those tables because the hazard now is of NBC 2020 is calculated directly for the site conditions that you have at your site. And the preferred way of representing that site effect or the site conditions is a metric called VS30, so a parameter called VS30. It's the average shear wave velocity in the upper 30 meters of your ground profile. Now, how we accomplished this, how we were able to get rid of those tables was because the recent ground motion models that are used in hazard models include site terms. So, and they include site terms in terms of VS30. So therefore now is when you go to an Arcane website for accessing seismic hazard values for a given location anywhere in Canada, you not only enter the location in terms of address or latitude and longitude or even pick it on a map, you also have to enter the S30 value so that you get your hazard directly for that site condition. Now, what are ground motion models that we've been talking about? They feature prominently up until here, mainly because they're one of the fundamental causes of the major changes in the hazard values. Ground motion models are basically a description, quantitative description of the level of expected ground shaking at a given location for a given earthquake magnitude and distance. So an earthquake that happened at a certain distance and with a certain magnitude will cause a certain amount of shaking at a location of interest. And so the ground motion models quantify that by basically describing how or modeling how ground motion waves propagate through the Earth's crust and how they decay by distance. These days, these ground motion models are mostly data-driven, with the exception of Eastern Canada, Eastern US kind of conditions where there's still quite a bit of modeling-based or simulation-based ground motion models due to the lack of the amount of data that is available, recorded data available in the East is quite a bit less than data available in the West. And that's because of earthquakes happen more frequently in the West compared to in the East. Now, I should mention that when we talk about these strong motion data, most of the data that we base our hazard calculations in Canada are not from Canada. So we have some strong motion data in Canada, but not nearly enough to develop ground motion models specifically for Canada. So a lot of these models that we use and adopt are from other parts of the world, and the recordings are from other parts of the world, but we make sure that we adopt them in a way that is similar to the tectonic conditions in Canada. And they're also different. The way the ground motion propagates in a stable continental region kind of setting in Eastern Canada versus actively deforming crust in the West is very different. So the pattern and the speed at which the waves die down is very different between Western Canada and Eastern Canada. So that's one of the differences. So active shallow crust versus stable shallow crust. But the other, and in Canada, this roughly translates to west of the Rockies versus east of the Rockies. But also in a subduction zone, the waves propagate differently than any of these other two types of tectonics. So all of this has to be taken into account, and ground motion models have to be appropriate for those types of tectonics. Like I mentioned a little bit before, these ground motion models used to be developed for a few specific ground conditions. In Canada, we used only one reference ground condition. Sometimes it's rock, sometimes it's a different kind of ground condition. But more recent ground motion models started including VS30 based site terms, so which makes it easier to compute hazard directly at a specific site condition, rather than computing it for a general ground condition and then, or a reference ground condition, and then converting that to different site conditions, softer soils or harder rock, by using certain factors. So we no longer need those factors because we can compute hazard directly for the ground condition we're interested in. So what is VS30 then? So since we've been talking about VS30. So that VS30 is the average shear wave velocity in upper 30 meter of a ground profile. So this basically assumes that the near surface geology, so when we think of geology, of course, it's many, many layers of geology, different types of sediments, and then usually it stiffens as you go deeper, and then basically at some point you're going to hit bedrock. So this is a kind of a cartoon showing the situation in Vancouver, and this is simplified. So there's simplistically 3 layers of sediments, distinct sediments or distinct layers in and around greater Vancouver area. At the bottom is the bedrock, and then over top of that is ice age sediments who've been compacted by glaciation. So they're quite a bit more stiff and strong than the surface sediments, which are the more recent sediments after the glaciation. And therefore they're looser, they're softer, and they amplify the ground motion quite a bit more. So if we were to simplify this view, any given site in Vancouver will be a combination of these 3, or sometimes maybe directly bedrock or directly ice age sediments. But if we look at the top 30 meters of that ground profile, and we calculate an average shear wave velocity for these layers, and for many construction projects, these are done routinely, shear wave velocity measurements. So if you do that, and if you average it over the top 30 meters of the ground profile, then you get a VS30. So that's average shear wave velocity in up to 30 meters of the ground profile. Now, why do we use this metric? It's a very simple metric, easy to measure generally. And there's many methods to do it, some of which are just surface methods. There's no disruption of the ground or anything like that, fairly quick, not very expensive. And with this one metric, we're basically not just looking at what's at the surface, but also accounting for the near surface geology that mostly affects how we perceive shaking at the surface of the ground. And this is it's adequate for most soil types and most soil conditions. It's certainly not a bad metric for most of Vancouver, other than where we have really thick sediments at the Fraser River Delta. But it sometimes isn't the best in cases where you have a very shallow soft sediments over stiff bedrock, so very high impedance contrast. It's not gradually stiffening, but generally, bearing in mind, it gives us a nice, simple to use metric to characterize site conditions. Therefore, building codes have kind of evolved over time to consider this metric as the site characterization metric. Now, having talked a little bit about hazards so far, I'd like to switch gears a little bit now and talk a little bit about the performance goals in NBC. For the most part, NBC, until NBC 2020, has had a single performance goal. And that was different for each category of buildings, but importance category buildings, but there was only one for each importance category building. So for normal importance category buildings, this was life safety through collapse prevention. So it seems to come as a surprise to many people when they hear this, but the only goal of the National Building Code was to prevent life loss, not restrict damage, not easy recovery after a disaster. Those are much more secondary, and they weren't an explicit goal in NBC. The sole performance goal of NBC is life safety through collapse prevention. I should say was, because that changed now as of 2020, NBC 2020 a little bit, and I'll explain in a minute. But I just would like to say that that's for normal importance category buildings. High importance category buildings, we expect them to remain safe for occupancy after an earthquake. So these are buildings such as schools, community centers, where large people might gather after an earthquake if they have lost their residential buildings, safe access to their residential buildings. And the post-disaster buildings goal, again, single performance goal, but a different one, is remain usable for its original purpose. So basically, if it's a emergency operations center, we want those to be still somewhat operational. In practice, we don't know exactly, because these two highlighted categories, high importance category and post-disaster performance goals, were achieved by certain provisions in the code that we assumed if you did these, you achieved those goals. There was no specific check to make sure, yes, indeed, these buildings will remain operational or occupiable after an earthquake. And those were, so for high importance category buildings and post-disaster buildings, these goals are achieved through four major changes in the code, or provisions in the code with respect to normal importance category buildings. One is increased loads. So we design them for higher loads than normal importance category buildings. So that's basically a capacity. We give them a higher capacity to carry loads, seismic loads. The second one is reduced deflections. So deflections and the displacements of a building is what causes damage. So reducing deflections reduces the amount of damage you'd expect in a building. The third is restriction of certain structural irregularities. There are a few structural irregularities that very highly correlate with damage after earthquakes. So being cognizant of the fact that we would like post-disaster buildings to remain usable for their original purpose, we wanted to restrict these structural irregularities so that the probability of damage to these buildings is lower. And finally, minimum ductility requirements. So we certainly don't want these buildings to reach their capacity and then fail suddenly after that. So we want them to have extra capacity, some extra flexibility left after major damage to them if they sustain damage. So given this, and I'm going to go back to the normal importance category as an example. So for that one, our sole goal, performance goal, was life safety through collapse prevention. Now, in certain other codes, including US, these two performance goals are not considered equivalent. So life safety is different from collapse prevention. But in the Canadian code currently, in NBC, we categorize them as fairly equivalent. So we prevent collapse to avoid life loss. Now, a little bit, I'm going to get very slightly technical here, but it's a very simple curve, and I guarantee you this is the only structural curve you need to understand a little bit about earthquake performance of buildings. So this is what we call a load deformation curve. So on the x-axis, how the building deforms, and on the y-axis, how much load you're putting onto the building. And in this case, we're talking about horizontal load because we're talking about earthquakes. If you look at the first part of that curve, the blue part of the curve, it's linear, which means as I increase the load, the building is deforming more. But until I reach that point y, if I release the load, that building is going to go right back to its original position. So which means it's behaving linearly. So you load the building, it deforms, you unload the building, it comes back to its original position. So no permanent damage in that building. So up until the point y, which we call the yield point, until a building yields, it does not have permanent deformation. It does not have permanent damage to the load-bearing system. Now, that yellow part you're seeing is basically that changes after a certain level of load. If you keep increasing the load, you'll find that you'll get more and more deformation for the same amount of increase in load. And to the point where you reach U, at which point you don't even need to load the building anymore. It's just going to keep deforming and finally collapse. So basically that point U, what we call ultimate point, represents where the building collapses. So, and it becomes unstable and collapses eventually. So you don't need any more extra loads to deform that building anymore. It's basically reached a unstable position, and at which point it's very close to being collapsed. So in the NBC 2015, that was the only explicit goal of the seismic provisions, which was collapse prevention. So we didn't want the building to reach that point U, ultimate point, in its load deformation pattern. And we put that goal at a 2% chance of exceedance of ground shaking in 50 years probability level. So that was what we had. Now we implicitly assumed some damage control at higher probabilities or lower ground shaking. So if you increase the probability of an earthquake shaking, that means you're lowering the level of ground shaking, right? So we have lower the probability, higher the ground motion. But it was implicitly assumed. There was no explicit check required anywhere in NBC to make sure that, yes, indeed, we are controlling damage at lower levels of ground shaking. Now, what's changed in NBC 2020 is now we target 2 points on this curve. One is the yield point, beyond which the building is no longer elastic or behaving linearly. For each building category, so normal importance category buildings over a certain height, high importance category buildings, and post-disaster buildings, we now say at this level you don't collapse, but also at this level of shaking you remain elastic. So we're now limiting damage to buildings. In fact, we say you need to have no structural damage and remain elastic at a certain probability. That is higher probability than the 2% in 50 years, which is what we aimed our collapse prevention provisions for. So this is a huge philosophy shift from NBC 2015, and it's an important one, and it's a relevant one for seismic risk, because until NBC 2020, we built our structures to have any degree of damage, any amount of damage short of collapse. So any level of damage was acceptable as long as the building did not collapse. And it wasn't just us, it wasn't just Canada. This was generally the design philosophy in many countries in the world, in the US and New Zealand, everywhere. Now in 2011 Christchurch, and I show this as an example, we've had many earthquakes that showed us this, but I think 2011 Christchurch, New Zealand earthquake was a bit of a turning point for the engineering community, because it made us realize, well, what we're putting in our building codes is it enough? Is it acceptable? Because in this earthquake, buildings with as little as 10% damage within the cordoned off downtown area were demolished and rebuilt instead of being repaired. And not to mention that cordoned off downtown area stayed cordoned off for 4 years after the earthquake at least, so portions of it even longer. So the rebuilding took many, many years. So is this societally acceptable? From our building code perspective, there are two catastrophic failures that happened in Christchurch, New Zealand earthquake that accounted for most of the deaths, and both were built before 1980s. And before modern earthquake engineering concepts came into our building codes. So engineers could look at that picture and say, hey, look, anything built after we put these serious seismic provisions in building codes did not collapse. But was that enough when a significant proportion of downtown Christchurch had to be torn down and rebuilt? So is that really a successful outcome? So more and more realizing the society's expectations from earthquake design is perhaps different from how we perceived what we put into the building codes. And this is a major shift in thinking. And the NBC's new performance goals of remaining elastic at a certain probability level, and which changes by the category of importance, is reflective of that. Now, I also would like to pose this question: what is acceptable damage? Is repairable damage acceptable damage? And if that's the answer is yes, what is repairable damage? Now, this might seem a very simple question with a very simple answer to you, but for a structural engineer, repairable damage, to design a building for repairable damage is not very obvious. It's not a very obvious question. What amount of damage, what level of damage is repairable? Going back to that curve on the right-hand side, so that repairable damage will happen sometime after yield and before ultimate. But where on that yellow part of the curve we can say that damage isn't repairable is a very difficult structural or code-wise, codifying in a codifying sense, a very difficult target, performance target to define. Here's a picture on the left. This is from the 1971 San Fernando earthquake. Apart from the fact that please don't do that if you see a damaged building, the picture also says, hey, look, as engineers, look, we've had success with this building. It hasn't collapsed, so it's fine. It satisfies the code. But is that an exhibit? This building cannot be repaired. Its deformation is too high, and it's all concentrated on the ground floor. This would be incredibly difficult, if not impossible, to repair. So what is acceptable in this case with respect to codes versus with respect to our expectations as a society? So I'd like to wrap up this part of the presentation by saying NBC 2020 is a first attempt at limiting damage at lower levels of shaking with higher levels of probability. We would have liked to include all normal importance category buildings in this first attempt, but we weren't able to. So we tried to put something in without necessarily biting off too much in our first attempt. But that's basically the direction we'd like to go, is to impose these 2 performance goals as a minimum for all buildings as we go into the future. So that's kind of the direction we'd like to go, to more resilient buildings rather than just preventing collapse. Now, what about existing buildings? You're going to say, well, that's all fine and good for buildings that are built to NBC 2020, but what about all the, basically everything that is on the ground now? I'm happy to report NBC is working on an alteration of existing buildings, and I don't qualify what that is. So it could be a section in NBC current code. It could be a separate code. It's not very clear at the moment. Currently, it's being designed as a part of the NBC, but we'll see where it goes. It's a fairly new development. Alteration of existing buildings is starting to get some attention in the NBC process, so that's good news. And the seismic considerations are expected to be included in NBC 2030. So that's our target for NBC 30. So what for including the seismic considerations and for alteration of existing buildings. We hope that this will start shifting focus in NBC from mainly and not purely, but mainly from new buildings, because NBC does apply to major alteration of existing buildings already. But it addresses it by commentaries, not by actual provisions. So that's what's going to change in future editions of NBC. And like I said, the target for seismic considerations of that conversation is for NBC 2030. So just a quick look into the future to say that maybe if we're successful, maybe we'll start focusing on our existing buildings a bit more than we do right now. Now, the third part of my conversation is going to be about part 9. So what's part 9? What's up with part 9, first of all? So part 9, like I mentioned earlier on, was what's not new in NBC 2020, because it wasn't able to be updated. So I'll start with saying that everything I spoke about until now was under NBC Part 4. Part 4 is the part of the code that focuses on the engineering design as explicit seismic provisions. Part 9 is housing and small buildings. So they don't have engineering requirements. So these buildings do not have to be engineered in Canada. They have some prescriptive requirements any builder can follow to construct these kinds of buildings. Now, these are defined in the code as 3 stories or lower, and a footprint area of 600 meters square or smaller. Now, any building that doesn't fall in part 9 falls in part 4 automatically. Now, this dichotomy and the fact that the provisions and the hazard hasn't changed for part 9 buildings in NBC 2020 creates a little bit of a problem. Because virtually all our single-family homes and a significant proportion of our multifamily walk-up apartment buildings in Canada fall under Part 9. So most of us live in these buildings. So to me, it's very important that we need to examine closely what kind of protection gaps we're creating between Part 4 and Part 9 of NBC, and what kind of protection gaps are there, and what can we do about it. So a few notes on this. Certain parts of the country in Canada are exempt from lateral loads in Part 9. So Part 9, one of the things that I think absolutely has to go in Part 9 is that there's these exemptions. No such exemptions exist in Part 4 since NBC 2015, where we said a major damaging earthquake can happen anywhere in Canada. We're not going to exempt any part of Canada from seismic loads anymore. We'll put for parts of Canada where we have less seismicity, therefore lower chance of damage, we're going to put very simplistic lateral load requirements, but we still have requirements. So we've switched to that philosophy in Part 4 as of NBC 2015, but we haven't done the same for Part 9. So Part 9, if you look at Part 9, you'll find that a good portion of section of Canada is exempt from lateral loads in Part 9. So you don't have to do anything for seismic loads. Same thing for wind, actually, just as a side note. So Part 9 needs to close this protection gap, first of all. Then a certain configuration of buildings in Part 9 do not seem to have the same capacity, equivalent capacity as Part 4 buildings. So that's also problematic. So we try to make Part 9 a fairly simplistic, kind of prescriptive, simplistic requirements that anybody can follow. But at doing that, we shouldn't lose any safety to a proportion of our population. And the third thing is, some requirements that exist in Part 4 restricting structural irregularities that are highly correlated with damage is still not fully implemented in Part 9. So we need to take care of this. So, and speaking of which, one of them is Softstory. So a good performance, wood buildings show a good performance when certain problems do not exist, but when they do exist, they can cause a lot of damage and potential life loss. So on the left here is a tuck-under parking building in Victoria, BC. And here on the right-hand side is what happens to those tuck-under parking type buildings from one of the many examples from 1994 Northridge earthquake. So I hope you can see the cars there down below. So this building was a 3-story building. Now it's a 2-story building because it's completely collapsed over top of that Softstory. But it isn't even restricted to only apartment type buildings with tuck-under parking. Same Softstory effects were seen in kind of row housing kind of situations, but even single family homes. And these 2 examples are from 1989 Loma Prieta earthquake. So we know what happens to these buildings. We need to fix this in Part 9 because all of these buildings would have fallen under Part 9 in our code. And yet, as we improve part 4, we need to bring part 9 in parallel to the same level of protection. Just a quick note before I wrap up here. National Building Code of Canada. So I've been talking about NBC and the recent release of NBC 2020. National Building Code in Canada is a model code. So as it is, it's not law by itself. So it becomes law only when it's adopted by the provinces. So on the left-hand side, you see the National Building Code of Canada 2015 edition. It became law in British Columbia in 2018 when it was adopted by BC. Then, this is an example, every province adopts it at a different time scale. So this doesn't happen automatically everywhere the same way. 2015 NBC, if I'm not mistaken, has still not been adopted by Manitoba, for example. The only exception to this, that the building code becomes law when adopted by a province in Canada, the only exception I know of is the City of Vancouver. City of Vancouver has its own building bylaws. So the 2015 NBC then became BC 2018, BC Building Code, and Vancouver Building Bylaw 2019. So City of Vancouver, I give this examples of City of Vancouver because they're the only municipal jurisdiction I know that have their own building bylaw, and they base it on NBC and BC. However, to their credit, they've improved it from, they're usually more restrictive and more higher protections than what NBC and BC provide. One example is, as of mid-1990s, Vancouver Building Bylaw has basically nixed Part 9. So they've been building their single-family homes and other small wood buildings to fully engineered Part 4 provisions, not the prescriptive requirements. So that's significant closing of a protection gap in City of Vancouver only, sadly. I'm not promoting we get rid of Part 9 everywhere in Canada, but it has a very important role to play in our construction landscape. However, I think there are certain protection gaps that need to be taken care of between Part 9 and Part 4. All right, so finishing thoughts. NBC is updated every 5 years, and we all, and in this we, I include you, have an opportunity to make it better. There's a public review process. The code, if you go to NRC, National Research Council website, they will post a building code before it comes out for public review. So anybody can look at it before it comes into effect and make comments and have a say in what should go into our building codes. All our standing committee meetings are open to public. So I'm part of the Standing Committee on Earthquake Design, but they're also the same thing goes for Standing Committee on Housing and Small Buildings. These are all open to public. Again, on the NRC website, you can request attendance to any of our meetings. In fact, I'll tell you, a lot of construction industry attends these regularly. So we'd like people who have safety in mind to also have a say in the code process, not just cost implications. And finally, code change requests. Anybody, any citizen in Canada can request a code change. So you can fill there are some standard forms on the NRC website and require or request a code change. And each of these are taken seriously. Same thing with the public review process. Every comment we get from the public review process, we go through, we respond to, and if there's anything that we could do about it that we feel that can go into the next code cycle, we seriously consider it. So there's concrete ways in which you all have an opportunity to make the code better. And of the thoughts that I kind of focused on throughout the presentation, rethinking performance goals and moving from merely preventing collapse towards resilience of our buildings and our communities, I think is a big one. And like I said, I'm happy to report after many of you might have seen me make presentations before and say, hey, we need to go in this direction. And finally in NBC 2020, we did. We took a first step towards this. Identify and eliminate protection gaps in our construction codes. We should not have certain parts of our code have different protection than other parts of our code. We really need to focus on this, and also more focus on existing buildings to reduce seismic risk. And hopefully NRC's initiative on alteration of existing buildings will go at least a step in the right direction, and hopefully we can do more on our existing buildings, reducing risk to our existing buildings. I know there's a Q&A session now, so please, I'm happy to answer any questions. Also, feel free to write to me. If you have questions afterwards, you had some time to think about what you just heard. Thank you so much for your attention.
Thank you, Tuna. That was a great talk, very clear. We have a number of open questions. I'm going to pose them in order that they appeared, although I'll go through, I'll give the first question where people ask multiple questions, then I'll circle back to their subsequent questions after everybody's had a chance to ask theirs. So Richard asks, do all our geotech investigations now have to ask for VS30 in lieu of site class?
They don't have to, but we made it very attractive for them to do it, because in the code now you can still use site class if you like, but if you do, the engineers are told that they'd get within that site class, the range of VS30 for that site class, they're going to get the highest hazard if they use site class. So if they use VS30, almost certainly they're going to get a lower hazard, more appropriate for their site. Therefore, we encourage direct calculation of VS30 or measurement of VS30 at the site.
Thank you. Our next question comes from Dr. Paul Kovacs, the Executive Director of ICLR. He says, thank you. Do the new performance goals apply to seismic risk or all hazards like severe wind and fire?
Currently, it's only earthquake. And the main reason why is earthquake, as being termed a rare load, was the only one focusing only on collapse prevention. The rest are much more making the buildings perform as they're intended to at those levels of loading. So wind loads, for example, we don't expect damage from wind loads to start with, right? So a second performance goals may be appropriate. It needs to be thought through. But for earthquake, it was absolutely necessary and important, because collapse prevention is a very little expectations on our buildings. And as I mentioned, we can do better, and we should do better than just preventing collapse. Great.
Our colleague Bohan Lee asks, you gave an example of buildings with 10% damage being torn down and rebuilt. Is that reflected in the HAZUS of vulnerability and fragility information? For example, would this 10% damage be represented as 10% damage or 100% loss in the HAZUS models?
I suspect, and Keith, you would know this too, I suspect that 10% is certainly not considered a loss of building in HAZUS or any other commercial vendor models, risk models that I know of. So typically we consider, as soon as you hit 60 to 80% of damage, that's where we start thinking, okay, maybe this is too far gone, this building. We should, instead of using a terminology of 80% damage, perhaps we should just say 100% damage. So that's about 60 to 80% is where we typically do that. In New Zealand, the situation was very instructive, because this particular building I gave an example of was inside that cordoned off part of downtown. And there was so much damage around it that this building was unusable until that portion of the downtown was open for reconstruction. And in the end, it was decided to just tear down and rebuild. But that's a bit of an extreme example. So typically we expect that to happen a little bit higher damage levels, but I think our typical or traditional consideration of 60% even may require a rethink.
Right, thank you. Saber Fasul asks, are there any correlations between the transient and residual drift and repairability of structures? And before you answer that, let me explain to our non-engineering colleagues what that means. Transient drift is the maximum degree to which the building moves relative to the ground or from floor to floor. And residual drift means any remaining deformation, displacement of the building, that the second floor is shifted a little bit relative to the ground, even after the earthquake shaking is over. So again, the question is, are there any correlations between those measures of drift and the repairability of structures?
Possibly, but like I said, definition of repairable damage is very, very tricky, and it also varies by, so it definitely is some function of deformation, but also a function of material and construction type and the load-bearing system itself. So if we're going to define repairable damage, we need to define it separately for steel buildings, concrete buildings, wood buildings, and we need to define it in terms of perhaps some form of deformation, transient comparison of the transient versus permanent deformation. But I'll tell you this, just to tell you how challenging this is. In our current second performance goal addition to the code, we've selected remain elastic as the simplest to define. And let me tell you, it was not simple to define. Engineers were asking to us, okay, so you say remain elastic. Do you mean the entire building remain elastic, or all the specific load bearing elements to remain elastic? What do you mean remain elastic? And from a certain material point of view, the curve that I showed you, where it is nicely linear and then starts becoming kind of gradually going towards the ultimate point. Well, for some buildings, that's a continuum. There's no single part of the curve that you can say this is purely elastic. And so some of these considerations by material has been very challenging just to define that. So now imagine how much more difficult it is to define repairable damage. So yes, maybe, but it requires very careful thinking through what can be quantified that way from the deformation, the various metrics of deformation, but also different materials, how they behave, and not just by a single column or a single wall. We're looking at the entire building to remain usable and basically fundamentally not damaged in a building. Of course, even if the load-bearing system is still elastic, you can have a lot of non-structural damage inside the building too. So that's another question. Once the non-structural elements, who may be giving some additional capacity to the building, when they fall apart, what does that do to the structural load-bearing system? But that's another consideration. So it's complex.
It is complex, and
I wish I had a simple answer.
Yeah, there isn't one. And if I can add in one more little, stick my oar in there, repairability is really, it can come down to a question of how much you're willing to pay to repair it. So a building with anything short of collapse might technically be repairable. But, if it costs more to tear it down and replace it, its repairability is less an issue than how much it's going to cost.
That's right.
Okay. Next question is from an anonymous attendee who comments Alberta is having a lot more earthquakes, and the attendee chatted a link to a JPEG, but presumably the attendee is asking, what does that mean? What are the implications for, for risk, the fact that Alberta is having all these earthquakes?
Well, there are kind of two sources of those earthquakes, right? There's the mining and other resource extraction related induced seismicity in parts of Alberta, but there was an earthquake that was felt in Calgary recently. Turned out that has nothing to do with any of those man-made effects. So like I said earlier, in Canada, we have certain parts of the country have more frequent earthquakes than others, but there's no part of Canada that we cannot have a magnitude 7 damaging earthquake. So yes, it happens less frequently. So when it happens, it's a bit more of a surprise. So the earthquake in Calgary is an example. A lot of people felt it and they were surprised that there was an earthquake in Calgary. It was actually slightly outside of Calgary, but nevertheless, that doesn't mean that it's not an impossibility. It just happens more rarely, therefore attracts a little bit of attention. But like I said, in Alberta particularly, or any part of the country where there is resource extraction going on, we have known pockets of induced seismicity as well.
And this is a closely related question from possibly the same or possibly a different anonymous attendee. Oh, it's the same attendee, but since I started, I'll finish. Is there a potential for damage in the Rockies/foothills?
Absolutely, absolutely. The question is always tie that to what's the probability. So yes, there's potential and lower probability than say coastal BC, but yes, absolutely.
Great, thanks. Turning to Paul's next question, Paul Kovacs asks, is 2025 the target for the next revision of the code?
Yes, it is. So 2025 cycle has started. We're already working on the 2025 code, NBC. Now, what's coming in terms of seismic, it's not as major or groundbreaking as what we've done in 2020. So our goal is to continue to improve seismic provisions in NBC 2025, but I would say probably the more exciting next seismic related development will be in 2030 when we incorporate existing buildings into the provisions.
Great. Turning to Richard Annette's second question, given the experience in New Zealand, do you think downtown Vancouver will experience the same level of devastation?
I always draw parallels between Christchurch, New Zealand and Victoria, BC, because the downtown cores looked identical almost before the earthquake happened. Very, very similar. In Vancouver, if I were to draw a parallel, it would probably be something like Gastown. There were a lot of historical brick buildings, unreinforced masonry buildings in Christchurch, which is part of the reason why there was such widespread damage. However, the two buildings that collapsed that caused 90% of the deaths in Christchurch earthquake were both pre-1990s non-ductile concrete buildings. We have a lot of them in downtown Vancouver as well. So from that regard, perhaps we should be a little bit concerned. Now, like I said, in terms of wood buildings, as of mid-1990s, City of Vancouver has been very proactive in making sure all those buildings were engineered. And therefore, some of the deficiencies we talked about in the rest of Canada's wood building stock may not be as bad in Vancouver if they were built after mid-1990s. But the non-ductile concrete and unreinforced masonry for sure are a concern for Vancouver and wherever they concentrate, and there are quite a few of them in downtown Vancouver. Although lots of new ones being built as well. So there's a bit of a urban recycling going on in Vancouver, so which is good. But I'll say this too, even in the new ones, sometimes I'm concerned because we have this, I wanted to add a little section on structural irregularities in this talk, but I realized I already had a lot of material. So maybe another future talk, because structural irregularities, though they're highly correlated with damage in past earthquakes, and we know this, we know that they attract a lot of damage. It's not we are not handling this problem in a way that would, I think, better limit damage from earthquakes. So what I mean by that is right now we're kind of reactive to it. So we see some practice in engineering design, I should say architectural / engineering design, and then we add a new irregularity because, oh, all of a sudden, you know, this new style of buildings come into effect, and we cringe when we look at it because the latest one is, for example, inclined columns. Lots of vertical accelerations now you'll have to consider in addition to the horizontal. And the complexity of the dynamic response is quite a bit increased. So we, in the code, if you look at the different editions of the code, we keep adding new irregularities, structural irregularities, as architects and engineers dream up more structural irregularities as we restrict some of the old existing ones. So I think some of these things that we can certainly improve upon, instead of being reactive, we could perhaps define what's a regular building, instead of defining all these irregularities specifically, and say, if your building is not a regular building, here is what you must do. So that's something that one of the things that I'm working towards, in making the code a little bit more, not reactive, but proactive in limiting things that we know for sure are correlated with damage.
I'm going to ask a question of my own before I turn to the next question in the Q&A box. In the slide that you have on screen right now, you offer our attendees a variety of ways to participate in code development.
Please.
So my question, the more important part of my question is, do you think that this is sufficient? Does the public have a sufficient role in code development? I mean, these are the opportunities you've labeled, you've listed here are, we, the earthquake engineering experts and other building professionals, we've made these, you know, code changes and code change requests, and you, the public, can weigh in on them. Should there be some other role for the public, something earlier on, something related to setting seismic performance objectives, something that acknowledges the fact that, you know, it's the public's lives and livelihoods are at stake. It's their wealth and safety that are on the line. Do you think that they should have a greater role in setting the goals for the building code to reflect those preferences? And if so, how might that work?
The first condition for that to happen is information. The public needs to be informed, first of all, what their code is delivering, to then say, hey, well, that's not enough. Because virtually everybody I speak to, even some engineers, still aren't, even though they follow these provisions, they do not appreciate the fact that if they don't read the commentary of the code, people don't appreciate that all we are requiring of our buildings is not for them not to collapse in an earthquake. And also the thought that even if you design to no collapse, that's a 2% chance of exceedance in 50 years, which means there's still a 2% chance that actual shaking will be higher than what we designed our buildings for. So there's that too. And people don't think about the meanings of these. What does it really mean? What does my code do? So if a person from the public purchasing a building and built in 2015 would think that their building will be just fine to live in after an earthquake. That's their perception generally. So first of all, we need to inform everybody that, hey, our codes are currently delivering this. The other thing most people don't appreciate is that difference between part 9 and part 4. We have, in theory, same protection goals for both parts of the code, but in practice, we don't. And we need that communicated. And then maybe people will start saying, okay, well, we need you to improve this. So information of public, I think we need to inform them, first of all, what is there. And I totally appreciate the fact that in the public review process, we put out a code and it's very technical, and for somebody to just read it and absorb what its significance is and then comment on it is not a very easy task. So, so Keith, I think for this process to really work appropriately, for every code review, public review process, we need also a kind of a layman's description of what's our code doing, what are the performance criteria right now in simple terms, and put it out there and somehow have some public forum to talk about it and see if that's acceptable. That is, maybe people are happy with that and they don't want to pay more for buildings to be safer. I don't know. I mean, safety is not actually safety. We would like them to be safe, but maybe repairable or whatever other considerations they may have. So yeah, so I think code itself being out there, in fact, in Canada, we made it free too. So it's now downloadable by anybody. But that may not be enough. We need a simpler layman's description of what is in the code right now for that conversation to really truly happen.
Well, if you have an opportunity to start that conversation or to construct some sort of mechanism for that conversation to get started, please count me in. Next question is from Kyle, who asks, could Dr. Onur re-articulate the Cascadia subduction interface activity rate?
Right. So in simple terms, we in 2015 assumed the return period for a Cascadia subduction zone full rupture, subduction zone earthquake on the Juan Pico plate was roughly 500 years. New research has shown more events in some of the ocean bottom drilling cores in the subduction zone. So therefore, the 2020 NBC's assumption for return period of full ruptures Cascadia earthquakes is 430 years. So that significantly shortens the recurrence period, which means activity rate is gone up. So they basically have them more frequently than we assumed before. And therefore that increases the hazard generally for all of Southwest BC, where the hazard from those types of earthquakes impact communities. So Vancouver definitely has gone up because of that partly, and Victoria as well.
Great, thanks. Sujan Adhikari asks, hi there, as being the citizen of Nepal, even being underdeveloped country, we have code for all types of buildings like stone masonry and brick masonry, and also for reinforced concrete. What I'm not understanding here is why Canada does not have a code for their residential buildings, by which I mean not have a code for their residential buildings.
Okay, let me try to clarify a little bit.
Please. Yeah.
So in Canada, our NBC, National Building Code of Canada, is not specific to any type of building. It's any material building, because it only covers load calculations. So you basically use NBC, which then becomes adopted by provinces. But anyways, so that code, building code, what we call building code, is only for determining seismic loads, wind loads, any other types of loads. Then we have what we call material standards for each type of building. So we have concrete standard, steel standard, wood standard. So each of these different masonry standard. So all of these standards are then used for detailing the design that for loads that were computed using the NBC. So it's a little bit different. Some countries I know have all of them all in one code, but we don't. So we have the NBC code, National Building Code, for load calculations. And then we have design standards for each different material. And these are CSA standards. Canadian Standards Association publishes these for different materials. Now, the housing and residential is not a separate code. In the US it is. There's a residential code of IRC, International Residential Code, versus IBC, International Building Code. We don't separate them. We put them all in the same code, NBC. Basically, Part 9 is like the US IRC, and part 4 is the US IBC. But having said that, that section of the code, the reason why it's different from the engineered part of the code is because Canada is a vast country, a huge, spread over a huge geography. And there are many, many communities where you may not be able to find an engineer to design a building. It would be incredibly expensive to bring a structural engineer to design every single family home in all parts of Canada. Therefore, Part 9 plays a very important role in Canadian construction landscape. It's just that what I was alluding to is that we shouldn't have, we should aim to have the protection and safety goals for the entire code to be the same, which we aim for, but I don't think we're achieving in practice. I hope that roughly answered the question.
Kyle Bozarth has a second question that's quickly answered. How may we contact Dr. Onur? Do you want to switch to that slide?
There.
There you go. Thank you so much. Just a moment. Paul Kovacs asks, are further changes in performance goals expected or possible in the 2025 code?
Now, what we started with a subset of normal importance category buildings. Our goal is to bring all normal importance category buildings into that fold, but I'm not sure if we'll be able to do that in 2025. One of the problems, Paul, unfortunately, this code cycle dragged on a little bit. So 2020 code came out in 2022, early 2022. I'm still leading the writing of the commentary for part 4. So we just literally yesterday finished everything and sent the material to the editors. So now our focus can be fully shifted to 2025. So unfortunately, we have a bit of a shortened cycle in 2025. So we're not very ambitious for the seismic provisions, at least, of the 2025 code. Also, we're really excited about the alteration of existing buildings that is coming up, and the scope is given to us for 2030 in terms of seismic loads. So us, when I say us, I mean us seismic types. So that, along with additional performance goals for all of our buildings, not just a subset of the normal importance category buildings, is potentially possible for discussion. Now, the other thing is a third performance goal, right? I mean, now that we open that door, can we improve it even further by a third performance goal? I would say right now, very difficult, given how much trouble we had even defining a very simple one, which is remain elastic. So 2030 is ways away, so maybe, but I don't know for sure.
Thanks. Richard Annett asks, did Auckland's domestic properties experience the same level of devastation as the city center did? How do Auckland's codes for domestic properties compare with Canada's?
I'm going to assume that they mean Christchurch, New Zealand. Or is it Auckland or Oakland in California?
Oh, he's not talking about Oakland, California. He's saying Auckland, but why don't you assume you mean?
I suspect it's New Zealand. So I'll answer this generally for New Zealand. So New Zealand downtown core was closed for portions of it much longer, but at least 4 years, a significant portion of it. And that was mostly because of iron reinforced masonry. Now the suburbs of Christchurch, where there were single family residential homes, they also got damaged. The usual suspects were still the same kind of pattern of damage with the Softstory and cripple walls and things like that, what we've seen many times in California earthquakes. But the main cause of damage in the residential suburbs of Christchurch was from liquefaction. So I remember I was still with Risk Management Solutions when this earthquake happened, and I remember looking at this picture. All of there was an aerial picture of a residential suburb completely flooded, and our first thought was pipe broke somewhere, because it's all this water everywhere. Turned out it was all because of extensive liquefaction in the area. So that extensive liquefaction caused a lot of sand to come to the surface, and that sand plus water flooded homes and created a lot of cleanup kind of cost. So that was the main form of damage. But like I said, don't discount the sort of damage that happens with Softstory and cripple walls as well. But yeah, that liquefaction was to the extent we hadn't seen in other places. And part of the reason why was the earthquake was so close to Christchurch. It was technically right underneath the city, so it was less than 5 kilometers away. And therefore lots of vertical acceleration. So the vertical accelerations were quite high, pushing that, helping that water column with all the sand to come to the surface. So it was a bit of a interesting and maybe less common thing that we've seen in other earthquakes. But yes, there was significant amount of damage to single family homes as well. But like I said, there was an extenuating situation where that big amount of sand and water cleanup made up a lot of that cost.
And before I turn to the next question in the Q&A box, I'd like to ask another one of my own. So the 2020 code reflects higher hazard from newer ground motion prediction equations, ground motion models, and an updated estimate of how frequently the Cascadia subduction zone earthquake has an earthquake. The Cascadia subduction zone has an earthquake. So a higher likelihood and greater strength of shaking. Now the buildings that were built up until now, they haven't gotten any stronger, and the code isn't going to change that, which implies that with this new information, those old buildings are less reliable, less safe than we thought they were, than they were designed to be. Have you, or has anybody tried to quantify in any way how much less safe, how much less reliable these existing buildings are than we thought they were?
There's so many facets to that question. First one is I'm hopeful that this alteration of existing buildings part of the code will start triggering a lot of, well, more than it does right now, reassessment of those existing buildings. So that's why I'm so excited about it. It's currently, these kinds of reassessments are only triggered if you make a major alteration to a building. And that may stay the same, but currently there's no formal process to do it, which this part of the code will create that. So all these buildings that were built to inadequate amount of seismic hazard hopefully will slowly be reconsidered and reassessed. So that's one aspect. But Keith, you touch on something very difficult for us currently, even in the engineering parts of the code, which is the duration of an earthquake. So those Cascadia subduction zone earthquakes are happening more frequently, but also they have a much longer duration of shaking, strong shaking, than other types of earthquakes. Our codes are mostly based on lessons learned in California. So typically, whenever the US learned a lesson from one of those California earthquakes and changed their code, we were watching closely. So, and we build similarly in certain types of buildings. Not all of our buildings are that similar. Concrete buildings we build quite differently than the US, but our wood buildings learned a lot from California earthquakes. But California earthquakes are 20-second, 30-second shaking earthquakes. We have here a whole other animal. The Cascadia subduction zone strong shaking is expected to be at least several minutes, not seconds of shaking. So, so there is some research being done at UBC and other universities in Canada about this effect of how is it different when you look at the damage from these long duration shaking. But in any kind of meaningful way, we still haven't encountered for this in our building code. So the only time the duration of the earthquake gets explicitly included in design is if the design is complex in a way that the code requires you to do a time history analysis, which is very, very few buildings would qualify for that. So they would have to have certain types of irregularities, or they'd have to be designed by base isolation or some other energy dissipation device. So in these kinds of very special circumstances, we require time history analysis. But until we include in our design the concept of duration more widely, I don't even know if we can answer the basic question you're asking, which is, even for new buildings, are we accounting for damage from a very long duration Cascadia earthquake properly?
Right. Thanks. So Paul Kovacs asks, may the objective of alteration of existing buildings provide a standard to achieve the same performance in renovated buildings as are expected in new construction?
That's a fantastic question, and it's close to my heart, because currently in 2015, let's start the story. In 2015, we used to say that, like I said, there's currently, the code says alteration of existing buildings pays lip service to it inside the code, but really sends you to a commentary, which is not enforceable. So in 2015, that commentary said, if your existing building satisfies 60% of the capacity of a current newly built structure with respect to the new building code, 60% or more, you're okay, you don't have to do anything. If it's less than 60%, then you must bring it to 100% of the code. Now, that's what the commentary said, but in practice, you know what happened is engineers, very smart engineers, engineers would take that to mean, if I upgrade, let's say I upgrade got triggered, and I upgraded to 70% of the code, well, that's higher than 60% of the code. So now if I read it again, I satisfied the commentary more than 60% capacity, so I'm okay. So they would advise for cost savings to their clients to upgrade to 70%. So virtually all upgrades until the 2015 code came out were done to 70% of the code. Even though the commentary clearly said, if you have less capacity than 60% of the current code, upgrade to 100% of the code. So that was the situation before 2015. Now in 2015, we made it worse by hoping better from our code, and I'll tell you what that means. So people who are doing any alterations to their buildings were very wary of triggering a seismic upgrade. So our observation was very few buildings were being upgraded. So people would do anything not to read the code very carefully, not to trigger that major upgrade or major alteration to the building, so that the seismic upgrade wouldn't trigger. So some engineers in our code committee decided, well, maybe if we allow them to upgrade to an even lower level than 60–70%, then maybe all of these buildings that are just sitting there not being upgraded at all would, the owners would feel a little bit better about upgrading their buildings. So we're doing a social experiment right now. As of 2015, we put in there much lower. If you're voluntarily upgrading, you could upgrade to something like 30–40% of the current code. So that's as low as that is allowed. Wow. But that was mainly introduced to see if that would indeed encourage people to do more upgrades instead of not touching their buildings with the fear that they're going to trigger a seismic upgrade. So I don't know the answer to, it's only been 5 years. So I don't know if that achieved the intended consequence, but my feeling on this is that, and this is only my personal feeling that has nothing to do with the code committee or anything like that, is that when we upgrade, we should upgrade to 100% of the code. Because until recently, 100% of the code was life safety. And let me ask you, what's 60% of life safety? What's 70% of life safety? Can we go below life safety? In my opinion, we should not. So we should, 100% of life safety cannot be compromised in my mind.
Great, thank you so much. We haven't gotten through all of our questions, but we have run out of time. This was
Well, my
great.
email address is on the screen, so please feel free to write.
Awesome. Thank you so much for your presentation. It was a terrific presentation. And thanks everyone
Thanks for having me.
for attending. Stay tuned for our announcement of our next Friday forum, and have a great rest of your day, and have a great weekend, everybody. Bye-bye.
Thanks. Bye.